Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the concept of sampling distribution. We will also present an example where the sampling distribution we are interested in can be approximated by a normal distribution. Okay, so that's the plan. Let's begin. So, first, let me show you the definition of statistic. Okay? So take a look at it, right? So, basically, what I want you to remember about a statistic is that a statistic is a function of observed or observable random variables. Okay? Make sense? Now, examples of statistics. You have seen a couple already. So, statistics. Statistic. Example of a statistic. One, well, sample mean, right? Sample mean is just defined as this, right? So we have a sample of size n, right? We observed n instances of n realizations of a random variable, right? We add them up, we divide them by n, and that's our sample mean. That's an example of a statistic. Another one, the sample variance. So we know that in that case, what we have, the sample variance, is just xi minus x bar squared, well, x bar here, and then that difference between xi and x bar, we square it, okay, and we divide by n minus 1. That's how we defined the sample variance. But again, so remember, a statistic is a function of observable or observed random variables, right? So it's a function of the xi's. This is also a function of the xi's, right? Okay. Now let's talk about sampling distributions. Okay, so what I want you to remember about sampling distributions, right, is this: that a sampling distribution is the sampling distribution of a statistic, and that the sampling distribution of a statistic is another way of saying the probability distribution of a function of random variables. Okay? That's it. Make sense? Since a statistic is a function of random variables, a sampling distribution is just a fancy way of saying, oh, the probability distribution for that function. Yeah, that's it. Okay? Make sense? Now let's talk about an example. So sampling distribution. Let's talk about an example. So consider the following random experiment. Okay, random experiment. Rolling a die once. Okay, now let's define a random variable. Okay, random variable. We are going to have xi will be 1 if the ith roll is a 6. Okay, and xi will be 0 otherwise. Okay, make sense? Okay, now so let define P as the probability of seeing a 6. So this is our probability of success, if you will, right? So clearly this guy xi is a Bernoulli, something that we call a Bernoulli random variable, right? Okay, now it's another way of thinking about a Bernoulli is as a particular case of a binomial when n equals 1. Okay, okay, so let me just remind you, right, that the mean, the expected value of xi could be found like this, right? It's just your value, the value of the random variable, 1 times the probability of observing that particular value. So it would be 1 times p plus the other possible value, 0, times the probability of observing that particular value. And since you know, the probability of observing a 1 is p, the probability of observing a 0 is the complement. So that means that the expected value of a Bernoulli random variable is just p. Okay, so you could easily find the variance as well, sigma squared. You can do that later. But here, I'm just going to say that the variance for this guy is p times 1 minus p. Sometimes you'll see that we refer to 1 minus p as q. Okay? Okay. So we have our random variable defined. Right? So remember that we are trying to come up with an example of a sampling distribution, and a sampling distribution is again just the probability distribution of a function of random variables, or another way of saying this is a function of our sample, right? So our sample would be a set of n of these guys, right? We observe, we roll that die once, we roll that die twice, so on. We roll that die n times. So now we have a sample of size n. Okay? So now let's define, using those observed random variables, right? Or, well, observed realizations of this guy, of this random variable, of this Bernoulli random variable. Okay? Now let's define a statistic. Okay? So now, statistic. And remember, a statistic is just a function of your sample, okay, a function of these observable random variables. The statistic of interest in this case is going to be, let me call it Sn, okay? And it will be just the sum of these guys, okay? x1 plus x2 plus x3 plus xn, okay? That's my statistic of interest. So clearly it is a function of my sample. Make sense? Okay, or it's a function of these observable realizations of a random variable. Okay? Okay. So now that we have our statistic, we want the sampling distribution of Sn. Sampling distribution of Sn. Remember that the sampling distribution is just the probability distribution of that function. Okay? So let me just remind you that that's what we mean. Probability distribution of Sn. That's what we mean by the sampling distribution of Sn. Now, I take a look at this guy, right? So each of these guys are independent realizations of this kind of random process, rolling a die, right? So, and this guy, each of each of our xi's has a Bernoulli distribution. And we know that a Bernoulli distribution, or a Bernoulli random variable, it's a particular case of a binomial random variable. And we have a sum of n independent such variables, binomial random variables. So my intuition tells me, hey, I think that from sta258, I think that the sum of independent binomials is going to be binomial, right? So how can we show that? The fastest way to show that that would be the case would be using the MGF approach. So let me find the MGF of Sn and see if I am right. If the distribution of Sn, the probability distribution of Sn is binomial, right? Okay, so let's do that. Let me just say that. Let's find the probability distribution of Sn. So let me compute the MGF of Sn. First, well, by definition, the MGF of Sn is going to be the expected value of e to the power t times Sn, right? Okay. Now, just by definition, right, by the way we defined Sn, this is the same as t times x1 plus x2 plus x3, so on up to xn, right? Okay. Agreed? Now let's do a little bit of algebra. That is equivalent to just e to the power t times x1 t times x2 dot 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 t times xn, right? Okay. And again, a little bit of algebra. E to the power tx1 plus tx2 plus dot 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 dot, right, is going to be the same as the product of n exponentials, right? These guys here. Let me copy paste this. So you guys agree that these two expressions here are equivalent. We're just doing a little bit of algebra, right? Okay, now this is important. Since we have a random sample, right? When we say random sample, what we mean is that they are independent, okay? So by independence, the expected value of a product of independent random variables equals the product of expected values, right? So now I get to rewrite this like that. Okay, expected value of that product is the product of expected values because those random variables are independent. Okay, so now we take a look at that expression, the expected value of e to the power t times x1. That is just by definition the moment generating function of x1. And the next one is the moment generating function of x2. And so on. We have the moment generating function of xn, right? Now, well, all of these guys have the same distribution, right? They are identically distributed, right? Let me just say that. Not what I want. Xi's are identically distributed. Right? So they have the same distribution. So if I have the MGF of one, then the MGF of the second one is going to be the same, and so on. Okay? So now, let's take a look at your textbook. I think it's page 837 or 38, the one that contains the expressions of the most popular distributions. It contains the expression of the PDFs. In the case of the continuous random variables, it has probability mass functions, right? In the case of the discrete ones, okay, so it's 837, the one that has the discrete ones. So probability mass function means variances, moment generating functions for the most popular distributions. So if we have a Bernoulli random variable, what we said is that a Bernoulli random variable is a particular case of a binomial when n equals 1, right? So p times e to the power t plus q, that would be the MGF for our Bernoulli, right? So here we go. So p e to the power t plus q, right? That would be the MGF of this guy, the first one, but they all have the same distribution, so they all have the same MGF. So what we have is this p times e t plus q n times, right? The product of those guys will be just p times et plus q to the power n. Okay? Now, if we compare this with the MGF of a binomial, it is identical, right? So, by uniqueness, property of MGFs, we conclude that the sampling distribution of Sn, right, or which is the same as saying the probability distribution of Sn, is binomial with parameters n and p, right? That's it. Okay. So again, remember, sampling distribution is the same as probability distribution for a particular statistic of interest, right? So it's the probability distribution for a function of random variables, right? That's what we mean by sampling distribution of Sn. The probability distribution of Sn, right? In this case, Sn, the statistic of interest, was a sum. Okay, great. Now, how about we use R so we can see a graphical representation of the sampling distribution of Sn. Okay, we're going to do this for particular values of n and p, and we are going to be very interested in seeing what happens with the probability distribution of Sn, or the sampling distribution of Sn as n increases. Okay, so let's launch R. So let me just say that what we're going to be doing here is playing around with the sampling distribution of Sn, right? And remember that if you type that hashtag when you're using R, right, that is going to be ignored by R. That will be just a comment. Okay? Okay. So, let me create an object called X, and X will get this. Okay, a sequence that goes from 0 to 10. The distance between each of those guys is going to be 1. So what I'm going to be doing here is I would like to create graph, a graph of the probability mass function of a binomial with parameters 10, and p will be 1 over 6, because we were saying that what if we're rolling a die, right? So let's think in terms of a fair die, right? The probability of rolling a 6 could be different if that die was not fair, right? But let's think in terms of a fair die. Anyway, so let me show you, right? X is what we want it to be, right? 0, 1, 2, 3, so on, right? So now let's evaluate the probability mass function at each of these possible values, right? So to do that, we know that we can use the binom function, right? Which stands for distribution of a binomial, right? So we want to evaluate it here at x. The arguments that we need are, we'll need to know the size, meaning the n number of trials, and the probability of success for each of those trials. Okay, so let's plot x against y type. In this case, I want p as in points. The color will be blue, and PCH equals 19 because I like solid circles. Okay, so there we are. So that's a binomial with parameters n equals 10 and p equals 1 over 6, right? Okay. So we could add a main title that goes like this: main binomial n equals 10, p equals 1 over 6. Okay. Okay. Now, how about we change things a little bit? How about we increase the sample size from 10 to 30? Okay. Now let's do the same thing, but now let me change this. So since the only thing that I changed was the y, the x is the possible values, right? And we know that the support for a binomial is 0, 1, 2, so on up to n, right? Oh my god, then I have to change this. Yeah, okay. So let me change the x. Now they should be up to 30, right? Now y will be evaluating from 0 up to 30. The probability we're going to leave unchanged. Now let's graph. That makes more sense. Okay, better. Okay. And now I should change this. This guy is now with n equals 30. Okay? So now let me show you a series of such graphs. So that's the first one that we did together, right? So probability mass function, binomial, n equals 10, p equals 1 over 6, 20, 30, 40, 50, 60, 70, so on. So I'm leaving p fixed and we are changing n. Okay. As you can see, as n increases, these graphs, the graphs of the probability mass function of a binomial, or in terms of this new perspective that we are taking here, since we are interested in the statistic Sn, which represents the sum of n independent Bernoulli random variables, well then it seems that the sampling distribution of Sn could be well approximated by a normal, right? Okay. Well, now let's talk about another statistic closely related to Sn, right? But it is slightly different. So let's talk about a new statistic that we're going to be calling p hat. Okay? So let's talk about another statistic. Let me define p hat p hat will be this. We're going to define it as Sn divided by n. Okay? So if we think about the way we defined our statistic Sn, well, that is equivalent to the sum of the xi's, those xi's have, each of them has a Bernoulli random variable, a Bernoulli distribution, right? So another way of thinking about p hat is this: the sum of the xi's divided by n. But the sum of xi's divided by n happens to be also x bar, right? Okay. Why am I calling this guy p hat? Because, for instance, in our example, xi represents the number of sixes that we roll, right? So if I wanted to approximate the proportion of sixes that I'm going to be rolling using that particular die, well, one way of approximating that probability, that proportion, would be count the number of sixes that you roll, right? And you divide by n, right? So that's why we have this p hat. It's the sample proportion. But note that that sample proportion deep down is just an x bar, a mean, right? Why is this important? So recall that the expected value of Bernoulli is p. Let me copy paste this. Recall that the variance of Bernoulli is p times q, right? So this is x bar. So by the central limit theorem, right? So by the central limit theorem, we have that x bar is, well, if n is large, we have that x bar is roughly, so So x bar is roughly normal with mean mu. Let me, yeah. And variance sigma squared divided by n. And let me be very specific about the notation here to avoid any sort of misunderstandings. So that mu happens to be the mean of that new random variable x bar. So let me underline that the mean of that random variable x bar is mu, right? And that the variance of x bar is also related to sigma square, but it's going to be affected by the sample size, right? By n. Make sense? So we know by the central limit theorem that the mean of x bar is mu, the same as for a single observation. And then the variance of x bar is going to be variance of a single observation divided by the sample size, n. Make sense? Okay, but now, since we said that x bar and p hat are basically the same, that means that p hat is roughly normal Now the mean of p hat is mu, but the mean for that guy is p. Variance for that guy, p times 1 minus p. For one of them, but for p hat is, you know, p times 1 minus p divided by the sample size. Make sense? Okay. So, what we have seen here is this, that the sampling distribution of p hat can be approximated by a normal, right? So, by the central limit theorem, the sampling distribution, meaning the probability distribution of p hat, can be approximated by a normal distribution. Make sense? Okay. So, how about we test drive our result? Okay. Let me open a new one here. Let's go back to our lecture notes here and let's try and do the following example. So take a look at it. Make sense? Okay. So in this case, the parameter of interest is a proportion, right? A p. Okay? So, in this case, what we have is a random sample with 300 observations in it, right? And we have that kind of setting, right? We have a Bernoulli random variable. It's going to be 1 if the ith person is planning on voting for this candidate, right? And then 0 otherwise. Make sense? So we have a sample of size 300 from a Bernoulli random variable, right? We can assume independence between those voters, right? So it seems that the setting that we have should work for this. Okay. Now, the probability that we want to find is the probability that p hat, meaning the sample proportion, okay, is greater than 50%, right? If this guy's popularity, this guy's support hasn't changed. So we're going to be assuming that these observations come from Bernoulli with parameter p 0.52. Make sense? Okay. So something more. We are going to solve this using this problem. We're going to be solving using 3 different approaches. One, we're going to be using our statistic Sn and its sampling distribution. Number 2, we're going to be using p hat and a normal approximation. And number 3, we're going to be using Sn, a normal approximation, and something called a continuity correction. Okay? So approach number 1 to solve that problem. To solve that example. Approach number 1. As I said, what we're going to be doing here is using Sn and its sampling distribution, which is just a fancy statistical jargon for its probability distribution. We have shown that Sn, right, the sum of the xi's, has a binomial distribution. Okay, so that's what we're going to be doing to solve this problem. So let's go back and let's get the information that we're going to be needing to solve this problem. So first, sample size n equals 300, and p, we're assuming that p is 0.52, right? So n equals 300 and p is 0.52. Okay, and what we want is, if we assume that his popularity hasn't changed, then what is the probability that more than half of the sample, would vote for him? So what we want is the probability that p hat, right, because we're talking about the sample, is greater than 50%. Make sense? That's what we want. Okay. So let's try and find that probability. So we know, right, given what we recently did, we can think of p hat like this, like a sum of n Bernoulli random variables. Right? So let me just say that xi Bernoulli random variable with parameter p equals 0.52. Okay? Okay. So, how about we multiply by n on both sides, and then what we end up with by doing that is this. That's the same as the sum of the xi's being greater than 0.5 times 300, which is just 150. Make sense? Yeah? Okay. Now, remember that Sn, right, is the sum of the xi's, right? And also remember that we have shown that the probability distribution of Sn is binomial with parameters n, in this case 300, and p 0.52. Right? Okay. So that will be useful. So this is the same as the probability of Sn being greater than 150. Now, we could rewrite that as 1 minus the probability that Sn is less than or equal to 150. Right? Basic properties of probability. But that would be the CDF, the cumulative distribution function of Sn evaluated at 150. And why do I care about that? Well, because I can, using R, easily evaluate the CDF of a popular distribution like a binomial using, a built-in function in R, right? Okay, so let's use R to find that probability. So using R, so remember that if you want, let me clear this, okay. So remember that if you want to evaluate the CDF of a binomial, this is what you have to do. Use that pbinom function. You need the number where you want to evaluate the CDF, right? You need the parameter n size, in this case 300. You need the probability of success for each trial, in this case 0.52, but that is just the CDF evaluated there. What we want is 1 minus, right? So 1 minus would be this, right? So the probability that we wanted, the probability that the sample proportion was greater than 50% for that sample of size 300, is roughly 73.75%. Okay? Okay. So that's the first approach. Using the sampling distribution of Sn, meaning a binomial, right, we were able to find that probability. The probability that the sample proportion is greater than 50%. Okay. Second approach. What we're going to be doing next is using p hat and a normal approximation. Okay, so using p hat and normal approximation. Okay, so what we mean by that is this, that by the central limit theorem, p hat is roughly normal, right, with mean p, right? So let me just place it like this. Let me write it down like this: mean p and variance p times 1 minus p divided by n, right? Okay, but now since we're going to be using a normal approximation, at some point, if you're going to be doing things by hand, and I'm going to show you how to do things by hand and using R, but it's important to learn to do this by hand because your final exam will be, you know, your typical in-class kind of exam, so you have to learn to do this by hand, okay? Anyway, so since at some point we're going to be using a normal approximation, that means that at some point, if you're going to be doing things by hand, you will need to use a table. And to use that table, you need to standardize this guy. Okay? So, here we go. That is, I'm going to rewrite this, but in terms of standard deviation, right? So, standard deviation is going to be the square root of that guy. Okay? Okay. So, let me remind you that what we want is to find the probability that p hat, the sample proportion, is greater than 50%. That's our main goal. Okay. So, what we're going to be doing here is, well, I'm going to use the fact that this guy is roughly normal, right? So this is going to be roughly the probability, and what I'm going to be doing here is standardize p hat. We have to subtract the mean, which is p. We have to divide by the standard deviation, meaning this guy, right? Make sense? Let me change it here. There we are. Okay, greater than, and let me do it on the right hand side with numbers. P is assumed to be 52%. We are assuming that the popularity of this guy hasn't changed. Then we are going to have 0.52 times 0.48 divided by 300. You guys agree? Okay, let me just write it down. Okay. So now what we have on the left hand side turns into a normal 0, 1 greater than, and then what we have is we have to do a little bit of algebra, right? Let's do it. So what we need is a numerator 0.5 minus 0.52, denominator square root of 0.52 times 0.48 divided by 300, right? And then numerator divided by denominator. So this is what we have, right? Roughly. And let's round it to 4 decimal places. Okay? Round to 4 decimal places. There we are. Okay? Make sense? Okay. So let's do this using our table first, and then we're going to check our work using R. So this would be the same as 1 minus the probability that the normal 0, 1 is less than or equal to this, right? Agreed? Just by basic properties of probability, right? Now, note that the probability of a normal being less than negative 0.69 is the same as the probability of a normal being greater than the positive version of 0.69. And I'll tell you why I'm doing that in a second. Okay? So by symmetry, that's the same, right? Let me just write that down. Z is symmetric. Okay, so why did I do that? And this would be the positive version, right? So again, so note that this guy is symmetric, so the area to the left of negative 0.69 is the same as the area to the right of positive 0.69, right? We're just using the symmetry. Why am I doing this change? Because I'm going to be using that table from your textbook, right? And that table gives you areas to the right. So I think that's 848. Yeah. Okay. So let's find something as close as possible to 0.69. So 0.69 is this, right? But again, take a look at this graph here. That table will give you areas to the right. So that 0.2451 is the area to the right of 0.69. Okay? So here we go. So using our table, what we have is 1 minus 0.2451, okay? Or in other words, 1 minus 0.2451 that's what we have using our table. Using table. Now let's find it using R. Okay. Let me clear this again. Here we go. So P-norm is going to evaluate the CDF at a particular point, right? And note something interesting here. What we're saying is that P hat is roughly normal with mean P and variance this, or P hat is roughly normal with mean P, again 0.52, and standard deviation the square root of P times 1 minus P divided by N, right? Okay, so what you could do is just, oh, do we still have that? Numerator? Yeah. Denominator? Yeah. Oh. There. Right? So the denominator, right, was this guy, right? The square root, when we standardized, the denominator was this guy, what we used to standardize, right? But that happens to be the standard deviation, right, of P hat. So what I could do to check our work using R is this. Oh, okay. So using that P-norm function, right, what I want to do is seeing if P hat is greater than 50%, but P hat is roughly normal with mean 0.52, right? So I want to evaluate at 0.5. The mean that I want is 0.52 P, and the standard deviation that I want is that denominator that we used to standardize. So standard deviation will be that denominator, this guy, 0.02888, and so on, right? Okay. So, but now we want 1 minus, right? Because this guy, right, we want this is what we want, the probability that P hat is greater than 50%, and this is going to give you the probability that P hat is less than 50%. So what we want is 1 minus, right? Because remember, this is the CDF. Okay? Okay. So there we are. Using R, we have this, 0.7559. Okay? So really close. The only thing is that we, if you're using a table, you have to settle for 2 decimal places, right? So anyway, we are on the right track. So let me just say this. Using R, using R, we have that. Okay? Okay. So now let me just point something out. Remember that we did this, our first approach was using the probability distribution of Sn, right? No, this is not the one I want. It must be the other one. This one. So it was 73.75% using the probability distribution of Sn, and the probability distribution of Sn is exact. There is no approximation. We showed that the probability distribution of Sn is exactly binomial, right? So 73 point something %. And here using P hat and that normal approximation, we are off by 2%, about 2%. and we have a really decent sample size, 300. So what we're going to be doing is trying to make that normal approximation better, and that's going to be the last thing that we're going to be doing in this video. Okay, so here we go. Let's do that continuity correction. Okay, so let me show you that in our lecture notes, but let me find it. Give me just a sec. Okay, I found it. So in our lecture notes you'll see this. This would be the approach number 3, right? What we're going to be doing is using p hat, a normal approximation, plus something called a continuity correction. Okay, so we proceed as before, right? The probability that p hat is greater than 50%, we express p hat in terms of you know, a sum of Bernoulli random variables. Then we solve for the sum of xi's. So what we have here on the right hand side is the probability that the sum of the xi's is greater than 150, right? Then using basic probability properties, this would be the same as 1 minus the probability that the sum of the xi's is less than or equal to 150. We have already shown that the sum of the xi's has a binomial distribution. Okay, but now, and this is the small detail that is going to make our approximation, our normal approximation, more accurate. Instead of evaluating at 150, you're going to be adding a 0.5 here. Okay? And when you do that, the approximation is going to be better. That's what we mean by a continuity correction. Adding that 0.5 here. Okay? And then what you do is, once you're there, just go back to your p hat, okay, and standardize. What's the mean of p hat? Is going to be p, 0.52. What's the standard deviation of p hat? 0.0288, so on, right? And you standardize, turn it into a normal, right? And either use your table or R, right? Okay, so let me show you what we have here on the next one. So using R, you have 0.7374, right? And this is so much better. This is closer to what we got using, you know, the exact distribution of Sn, right? 0.7375, right? That was using Sn and that sampling distribution, which was binomial. That this is an exact probability, and this one would be this one would be the approximation. So really close. Okay, so much better. So let's summarize what we did. Okay, so what we did here in this video is we talked about the concept of sampling distribution. But sampling distribution is relative to a statistic, right? And what is a statistic? A statistic is a function of random variables, and sampling distribution is just the probability distribution of that function of random variables, right? In one case, we talked about an example where we can find the exact sampling distribution or probability distribution for a function of random variables, for a statistic. In that case, it was a binomial, right? Okay. Then we talked about another statistic, p hat, the sample proportion, and in that case we couldn't get the exact sampling distribution of p hat, but we were able to approximate it using a normal distribution, using the central limit theorem. And then at the very end, what we said is that if you're going to be doing this, right, approximating the distribution of p hat with a normal, what you could do to improve your approximation is use something called a continuity correction. Now let me just mention one last thing, and then I will let you go. Give me just a sec. Okay, I'm back. Final comment about this. If you want to use this normal approximation to a binomial, right, it would be a good idea to check something like this. The approximation is going to be decent if n times p and n times 1 minus p are greater than 5. Okay? Another way of checking is this: n greater than 9 times the larger of p and q divided by the smaller of p and q. Okay? And this you guys already know, right? That the expected value of a binomial is n times p, that the variance of a binomial n times p times q. Okay? Anyway, just the final comment was this, that you could use one of these two guidelines to see when this approximation is going to work well. Okay? So anyway, basically the idea here is to show you that the central limit theorem can be used to approximate some interesting sampling distributions, okay? Probability distributions for statistics of interest, like the sample proportion. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.